We're going to do this is part 3 for this chapter. I'm adjusting my Zoom controls behind the scenes. In part 1, we did this. In part 2, we did sections 4 and 5. Hopefully, we'll get sections 6, 7, 8, and 9 done. Let's just get going with it. We'll see how far we get. Oh, past all that. Oh, yeah, no, we haven't done hydrolysis. We're right around in here. That was where we left off. Oxygen nucleophiles, we finished. I'm ready to start nitrogen nucleophiles. I'm having such a long Zoom day. I'm just, wow. It's too much Zoom. Where's the start button? Current slide. We will be looking at that same reaction mechanism. This is a good one. Remember these two from the previous video? If it's an acid, protonate it first and then do nucleophilic attack. And then you will need another proton transfer in the end to get rid of that positive charge. Otherwise, that would have been a leaving group. In base, there's no source of protons around, so don't start with a proton transfer. Start with the nucleophilic attack and then do the proton transfer to get rid of that or to balance out that negative charge that you brought in. So bear this in mind because this just keeps going over and over and over. We just substitute different things for the nucleophile. And then otherwise, it's this very same mechanism over and over and over and over. So when you start with a primary amine, you're going to get an amine. You're going to get an amine. If you start with a secondary amine, you're going to get an enamine. We'll see how the transcription service that goes with Zoom manages to handle those. Mechanisms are similar, except for the proton in the last step. Yeah. So you see how this just kind of goes dash, 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 dash. What's happening here between the ketone and getting to the amine? What? It's not showing me anything. It's the very same mechanism that we went through before, just with a different compound as the nucleophile. So all those little arrows, arrow, 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 that's taking you through these steps. So on this slide, this graphic that's from your book is just trying to kind of illustrate they're the same until you get to the very end where you're taking off that last proton. And it's trying to emphasize what's different about the last proton removal. With the primary amine, notice the nitrogen is at the end of an R group. So think something like, you know, N. And then it's got to have 2 hydrogens on there and a lone pair. So that's this one. Versus the secondary, notice that means there's 2 R groups. So here's the N. And then there's 1 R group and there's another R group. They don't have to be the same R group. and then it's got a hydrogen attached, and then it's got a lone pair. So these two R's don't have to be the same. It doesn't have to be a symmetrical molecule. And that 2 that's right there, that just means you have 2 different R groups. Would it be better for you if I called these RA and RB? And like one of those would be A and one of those would be B. It just means that that nitrogen has R groups in 2 directions and only 1 proton attached. So the primary has 2 protons attached to the nitrogen. The secondary only has 1. So once we get to this stage, notice this is very similar except for that proton. Well, what happened to the other one? That's already been taken care of. It's already come off. Here we're at the last step. So it's already lost 1 proton and now only has 1 left. Right down here with the secondary, by the time we get to this phase, we have no protons left on the nitrogen. It's an RA and an RB. So here's the thing, when it comes to the last proton transfer step, the secondary didn't have a proton left on the nitrogen itself to take off. There's no protons left there. So it has no choice on the last proton step, but to take 1 off down here from a neighboring carbon. This is representative of the same molecule you started with. Doesn't absolutely have to be, but you know, it's all in the flask already anyway. And it's taking off 1 at a neighboring carbon, giving you a double bond in the end. And a single bond to the nitrogen. So you have a carbon-nitrogen single bond and then a carbon-carbon double bond. Compared to starting with the primary, which still has a proton on that nitrogen, and that will be the proton of choice to be removed. That allows for a lone pair to come on into that nitrogen. And so here we still have a carbon-nitrogen double bond. Let's see, I don't know what color to use for that. So you're looking at that difference between having the carbon-nitrogen double bond versus a carbon-nitrogen single bond in conjunction with a carbon-carbon double bond. So do you think that if you were doing IR on these compounds, you could tell them apart? Hopefully you answered that. Yes, I could absolutely tell them apart via infrared radiation analysis, because this would have a carbon-nitrogen double bond stretching frequency. This one would have a carbon-nitrogen single bond stretch and a carbon-carbon double bond. So they are very distinguishable from each other. Even if this R group are all the same R group, they're very distinguishable from each other via IR. So keep in mind that you have 2 very different products, even though you're starting with a nucleophile that's, you know, they're both nitrogen nucleophiles. Okay, so that's just focusing on that last step. Clear all that. And move to the next slide where we'll go through the mechanism in more detail. Here's the secondary. So we know in the end, we're going to have a carbon-carbon double bond and a carbon-nitrogen single bond. And like I said, the mechanism for the other one is going to be, well, that one's different. That's a different molecule. Whoops, wait a minute. If we were starting with the primary, all of this is going to work the same until you get to the last proton transfer step. This step here was what was being explained, or at least drawn out in different detail on this slide. Okay, we're having nucleophilic attack first because this one isn't being done in the presence of an acid. Why to not do this in the presence of an acid? Kind of looks like here it's being done in the presence of an acid. Yeah, as a catalyst. Remember, some of these work in both acid and base. You would want the acid in a separate step, not in the same step. So you wouldn't want it to be this kind of thing. Like with them being together. You'd want them to be kind of in separate steps, ideally. Because this is a base. These ammonia compounds, these nitrogen compounds, they're basic. And you don't want to just have an acid-base kind of deal going on. It's a competing side reaction. So let's start with the nucleophilic attack. There's the lone pair. And then after this, we'll need to do a proton transfer. So now we can bring in, some acid maybe here, but that's a separate step. So intermediate is protonated, remove the negative charge. And in this case, we're going to do another proton transfer. So it starts out, right, like this. But because of the nature of the nucleophile we were using, right, the one we started with when it's a nitrogen, it didn't have a negative charge on there already. It wasn't hydroxide that has a negative charge. It was a secondary amine. It didn't carry a negative charge on it. It just had lone pairs. And because of that, right, it's going to end up with one proton too many. Whoops, one more. So we have that negative charge that comes at this point. Notice there's a positive charge on the nitrogen. So here's your conservation of charge. There was no charge in either of these starting molecules, but here we have a separation of charge, positive versus negative. So let's take the negative one and come over and do proton transfer and protonate it. And then we'll do another proton transfer to get to quench the positive charge down here, where we lose that proton. And this is why when we get to the carbinolamine, we don't have a proton here to take off because we just lost it right there. Now, let's continue because we haven't quite gotten down here, but see, this is where that proton disappeared to, way early in the mechanism. That proton right there disappears way in the early stages of the mechanism. It is nowhere to be found by the time you get to this part. It comes off way early. In this case, in the primary case, one of them comes off way early. And then one is left because it had two. But you lose that proton right there from the nitrogen way early in the mechanism. So let's do another proton transfer because we have an OH group here. So let's convert that into a good leaving group by doing a proton transfer. Once we have a leaving group out of it, that will come off. And then here's the lone pair from the nitrogen going in to form that double bond. So loss of a leaving group. Now, at this stage, which is where this one picks up, we're going to look at this very last step, starting from here. If it was a primary amine, you would deprotonate the nitrogen. If it was a secondary, like what's explicitly shown, right, take the proton off the neighboring carbon. Okay, using a diamine instead. So let's take the ketone and use a diamine, right, followed by a Wolff-Kishner reduction, we can get to an alkane. We can get to the alkane. So here's the diamine after it's been attached. It's like, well, how did it get attached? Just change that nitrogen molecule to be a diamine. Once you have it to this stage, so it's got the double bond to the nitrogen, the lone pair, and then a connection. It's got the double bond to the nitrogen, a lone pair, right? Well, that one, not quite that one. Look at this one. Here, the double bond to the nitrogen, there's a lone pair that's not shown, and then it has a connection. So for the diamine, right, they're just replacing that with an N, which can then go on into an R, some other R group. I hope you see what I'm saying. That's where this is picking up. There's no proton left here, but there's protons here. So we'll take one of those, giving us a resonance stabilized intermediate. So there's two lone pairs on that nitrogen at this point. And so that's going to allow for resonance to go through here. What's really useful about this is that you're now able to introduce a negative charge character to a carbon that once upon a time had positive charge character. When it has positive charge character, you have to bring a nucleophile in. Once it has negative charge character, you could go do other kinds of chemistry with it. And you don't have to go this route. You could do other forms of chemistry where you brought in an electrophile. In this slide, we're still just going to continue. Here's water molecule. So let's do a proton transfer. So there's the two carbons. We'll take the lone pair. It's not showing here because it has a proton attached to it. There it is. Yeah, I'm kind of off my game because of all the Zoom meetings I had to do in between the two recording sessions. Oh. All right, this connection is this. And then you can see how the top of this molecule, right, still looks here. The other resonance form isn't doing this, just this one that has the carbanion character. And then we'll do another proton transfer. Get rid of that proton. And you're like, why? Why are we doing this? What is here's the driving force. Having done this other proton transfer, we're now going to form a triple bond, a nitrogen-nitrogen triple bond. Now we can't overload the valence electrons, the octet, For the other nitrogen, because it's it's in the row n equals 2 on the periodic table, doesn't have access to expanded octet. We don't want to overload that octet, so we're going to have to break a bond right there. We'll put a lone pair here and give that carbon, once again, anionic flavor. But this part right here, this is the driving force. Because this is kind of a weird way to show the leaving group going off. What you're used to seeing when loss of a leaving group is you're used to seeing this arrow going the other direction, leaving behind a cation. But not in this case. And this is still a loss of leaving group. The two nitrogens are coming off as nitrogen gas. Oops. Nitrogen gas comes off. So even though the arrow is going in a different direction than what you're used to seeing, but you're used to seeing it like this, where the arrow comes from the bond and goes towards that leaving group that's leaving. That's what you've seen like 99% of the time in your chemistry studies so far. But this, it goes the other way. So then you'll have nitrogen gas come off. You notice here, the carbanion is not thermodynamically favored. It's a high energy product, but the driving force is the formation of this nitrogen gas. When that comes off, that leaves the reaction flask, and there is no going backwards. Notice that we went from equilibrium arrows at each of those previous stages to a one-way arrow. Le Chatelier's principle, and it's not going to go back on. Once you have nitrogen gas, it's not going to like spontaneously react. Nitrogen gas is very inert gas. So it's not going to just come along and chemically interact with these things. That nitrogen-nitrogen triple bond is one of the strongest bonds that we see in nature. So this comes off as a gas. It's not going to do any more reactions. And then since that's leaving, Le Chatelier's principle just pushes us all the way to the end. So this is the driving force for all of this going on. We've got that carbanion, and then we'll do another proton transfer. So what you've managed to do in this method is completely take a functional group out of your molecule. So if you had a ketone and you needed to remove the functional group completely, but for some reason you couldn't just, you need to find some way to get that oxygen off of there. Here's a way to do it. And you're left with just an alkyl chain, just an alkane. Notice the nitrogen's not even there anymore. So this isn't the starting material. The starting material, right, was this. And then we'll do the dashed arrows, kind of like they do. I'm doing that shorthand. You're starting with that ketone and able to get rid of the carbonyl out of it. It's a very difficult thing to do, but here's a way to do it. Wolff-Kishner reduction. Whoops, that's the name of this process. Wolff-Kishner reduction. Okay. Hydrolysis of acetyls, imines, and enamines. Some of the previous mechanisms were reversible. The intermediates are the same, but you have different steps going backwards. So the intermediates in each case So molecule 2 looks like molecule 2, whether you're going to the left or coming back to the right. Whether this reaction is going or coming, molecule 2 looks like molecule 2. But how it gets to be molecule 2 will look different. The reaction step. Is it a proton transfer or is it a loss of a leaving group? Because to get molecule 2, in one sense, you're getting it from molecule 1, going that way. If you're coming back, you're getting to molecule 2 from molecule 3. So that's what we mean by saying steps are different. But molecule 2 will look like molecule 2. Molecule 3 will be molecule 3. So the intermediates are the same. And then we've studied this all going forward, right? That was the hemiacetal, all the way to the acetyl. And then if you take the acetyl and you want to go back to the carbonyl, you're going to do a proton transfer first, and you're going to protonate one of these and turn it into a good leaving group. So this first step is the protonation step. So what does R look like? It looks like this, but with one of these protonated. That's what molecule 7 is. To get from 7 to 6, you're going to do the loss of the leaving group. So this is going to come off. So I'm going the backwards one. Because we looked at the forward direction in detail. This one is kind of looking at the backwards one. So we would need to have loss of a leaving group. Whoops, why isn't my pen working? In order to get us to molecule 6. And then molecule 6, we would do a nucleophilic attack, come back to molecule 5, do another proton transfer, and we get back to the hemiacetal. So hopefully you'll get kind of an idea of how this works to go backwards. Protonate the hemiacetal, we got to do a proton right here. This proton, add it here. One of the lone pairs from the oxygen. That'll turn that one into a leaving group, and then that will disappear. You'll get to molecule 2. And then do another proton transfer where you take that proton off to restore the double bond to get back to 1. I would put this graphic on my note sheet and be able to draw all arrows in intermediates. So you should go through and draw these intermediates and draw the arrows that goes back and forth. Like, well, wait a minute, I don't remember the intermediates. How do we remember those? You look at the PowerPoint that's on Canvas and go and draw your intermediates. So here was the ketone. Here's what we mean when it gets protonated. Here's what we mean when the nucleophilic attack is happening. Right? Here's where it gets protonated. Here's where the nucleophilic attack happens. So that molecule 2 what's this? Molecule 3. And then the hemiacetal. So molecule, oh, go one more. Molecule 2, molecule 3, and then the hemiacetal. Molecule 5, 6, and 7 molecule 5, molecule 6, molecule 7. So that's what you need to have on that note card. And then this is just going in the forward direction. And then what you can do, if you have this, like I would go onto the Canvas site and pull up the PowerPoint and print out a copy of that slide and then make notations on this slide. And then, how do you go backwards? Well, now you know that to go from 8 to 7, you need to add a proton. 7 to 6, loss of a leaving group. Oh, there we go. So, in other words, to go from here to here, like see the backward arrow, we have to add a proton. You'll need a source of protons. And then to go from here to here, from this one to this one, you're getting a leaving group off. The source of protons will put that proton there. And that's how you get to molecule 7. And then loss of a leaving group, see where I have the cursor moving, that will take that alcohol group off of there. And when the alcohol group comes off, right, then this lone pair can move in to reform that double bond to get you to molecule 6. From 6 to 5, there's a nucleophilic attack that needs to happen. Okay. Well, they line up really well with that slide, don't they? From 6 to 5, there's a nucleophilic attack that has to happen. What does that nucleophilic attack look like? It looks like water, the lone pairs, instead of subtracting water, see the subtraction was written on this side, meaning it's for this one. To go back the other way, you'd need to add water. So have water sitting around. Right, and do a nucleophilic attack. To attach the water molecule. That gets you to molecule 5. To go from molecule 5 to molecule 4, we're going to need to lose one of those protons. So molecule 5 to molecule 4 is going to be a proton transfer. Where the proton is coming off. And then 4 to 3, you'll need to add a proton. Protonate the alcohol group over the hydroxy group. Do the alkoxy over the hydroxy. Protonate that. And then to get from here to here, you're going to do loss of a leaving group, which you can't see because I have that number 3 drawn right smack on top of that molecule. You need to do a loss of a leaving group. That will break that bond off, and then this lone pair can come in to make that double bond. And then to go from here, that would give us this, right? And then to go from here to there, you'll have to do another proton transfer. See where the proton's coming off. So this big purple arrow is just put to emphasize to students that not only do you need to know the mechanism going from the ketone to the acetyl, you need to know how it works going from the acetyl back to the ketone. And so hopefully my kind of going back and forth between those slides helped you to kind of figure that out and how to work with that. And there's no substitute for you sitting down and drawing that mechanism out full blown on your sheet of paper. Print out the slide and draw those arrows on there. Mechanism on next slide. Oh, see, oh, it looks like I haven't looked at this PowerPoint in a while. Mechanism on next slide. Start with the acetyl and work your way back to the ketone. The amines and the enamines also go backwards. Right, the steps look a little different, but just reverse them. Like, what would you need to do to get from here to here? Well, this one has a proton that that one doesn't have. So you'd need to do a proton transfer to protonate it. How do you go from here to here? Well, notice that one has a water molecule on it that this one doesn't have. To go from here to there, you had loss of a leaving group, taking off a water molecule. So to go from here to here, you'd need a nucleophilic attack where you add a water molecule. To get that on there. And then to go from here to there, well, this has an extra proton that one doesn't have. So you would do a proton transfer with a base, like, you know, have some A minus around. I don't know, A minus, there's a lone pair, right? Have that do the proton transfer to get it back to here. To go from here to here, we need to add another proton. So remember that, see that lone pair? Have that go do a proton transfer. Source of protons and have that arrow come from here to attach a hydrogen. And then to go between these two, well, the difference is the proton up at the top. So you'd have to have something to come in and snap off this proton. And then from there, you're just reforming that double bond. So I guess you don't have to draw it all. I went ahead and drew it for you. It's in your book. I didn't draw it. I pulled the graphic from your book. But try to understand how each of these steps, at this point, all the arrows are probably starting to look alike. They are to me. These steps going this way, that's the backwards of this, is what we figured out when we looked back here and we did these going backwards. What do we need to do at each step? Notice I put the addition 3 page numbers in here. Protonation to convert that ethoxy group into a good leaving group. Loss of a leaving group, formation of that double bond. Nucleophilic attack, loss of a proton, converts it to an OH, and then protonation to convert the remaining ethoxy group into a good leaving group, and there it goes, and then a final proton transfer. Okay, sulfur nucleophiles. Look back at the alcohol information and replace the O with an S. That's the main thing that we're going to say about sulfur. See, then it goes to hydrogen. So think back about the alcohol mechanism and just replace R with S. And you'll go from the ketone to a thioacetyl. This slide. All you have to do is change the, not that O, this one. Change this oxygen to a sulfur. Throughout here. The ones that are on the ROH, change those to the S's, to the sulfurs. And you have the mechanism. If it was a dithiol, right, where you have 2 sulfurs on there. Then you form the cyclic compound, just like we talked about earlier when we said, what was that? We said that. Was it here? Was it? No, I think it was on this slide. Yeah, it was on this slide. Where we talked about how if these were connected, right, if you had some R in between the alcohol groups, I call that RM. And then this could be like a whole different R group there. And we talked about how RM would connect them and you'd end up with a cyclic compound. That's in the previous video. Similar thing can happen if it's a dithiol, forming this cyclic thioacetyl. Now here is one little difference. Notice you can take this off using rainy nickel. That goes back to last semester. So just look in last semester's notes. I don't want to go through all those details in the context of this. That's just something to go quickly review. I wouldn't test you on the details of the rainy nickel reduction. That was last semester. Here, it would be towards the end of the semester where we were doing the thiol chapter. But notice the reason that this is in here and it's very synthetically useful to keep in your mind is because, like in your toolbox for synthesis, it allows you to get rid of the carbonyl functional group entirely, get that oxygen off. And you're taking a molecule that was highly reactive and converting it into an alkane. So we've seen 2 ways now to get that oxygen off. One is using a dithiol. The other way was with the nitrogen. In my face-to-face tests, there's always one question that has at least one mechanism question, right, that will have this in it, where the nitrogen is coming off. I don't have an online test for this written yet. I'll have to write that, but just be aware that's something that I do like to put in a test, something where the nitrogen gas will come off of there. And then I think we'll do hydrogen nucleophiles, and then we'll stop this presentation. Well, how long has it been? How long have I been? Yeah, I've been going on for a while now, so we'll stop it after the hydrogen nucleophiles. Ketones can be reduced to alcohols. This reference, right, lab students, what reaction is done this Wednesday? This was that reference to the, Gigi, what are you doing, baby puppy? Oh, it must be getting near dinner time. No, they still have a ways to go for dinner. Sorry, my puppy's walking around kind of looking for some treats. Oh, great. I said the T word. Now she's sitting up and begging for a treat. Oh, okay. Oh, sorry. Gigi, no, baby, doggy, you're so cute. Oh, no. Okay, I digress. This reference to lab on Wednesday, I'm so sorry, students. The lab students, that's the one where it was referring in that semester where we were face-to-face and we were doing the borneol to camphor, where camphor has that double bond in it, to isoborneol. And so that's where this fell in that semester. And lab students in spring 21, we will do that reaction in lab when we start meeting on campus face-to-face next week. But that's not your experiment for next week. We just start back next week. So you can check the lab schedule for when we have the borneol camphor isoborneol. That's what that reference is. What does LAH stand for? Do you remember? That's lithium aluminum hydride. Lithium aluminum hydride. I don't know why alchemists chose to write it this way. Probably for the same reason that we'll write benzoic acid, we'll just sometimes put BZ, HBZ for benzoic acid. Yeah, it's a very shorthand kind of a way to write something. Or when they start drawing phenyl rings like that. And water. And you're taking the carbonyl and converting it into an alcohol. And then once it's in an alcohol, then this goes off and does all those reactions in the alcohol chapter. Where's the alcohol chapter? It's at the end of semester 1. On your textbook. Oh gosh, I don't remember what chapter that is in your edition of the textbook. You know, it's like, I want to say it's somewhere around like 12, maybe? Chapter 12-ish. The one on oxygen and sulfur that we cover towards the end of the semester. So, super synthetically useful because you can just protonate it and then go do all the alcohol reactions. Notice here, this just goes to the alcohol. It doesn't go to an acetyl or a hemiacetyl. It's not doing that. This is very different. If you have the alcohol and you want to come back, sodium borohydride and methanol. Sodium borohydride and methanol. Oh, I'm sorry. I was saying that, speaking, going, that makes no sense. Sodium borohydride is a reducing agent. Oh, God. I'm sorry, all these arrows are looking alike. It's a reducing agent. So I'm just like, why am I drawing this the wrong way? Right? They so usually put the backwards arrow underneath. I really need to stop this. This is the last slide. I'm sorry. It's a reducing agent. So that's another way to get to the alcohol. Oh, God, I suck. Oh, God. We're almost done. Just do this one last little piece. Here's our mechanism. Here's the lithium aluminum hydride coming in. See how it's the hydride ion that's going in there. It's H minus that goes in. And then you can do a proton transfer to protonate it. And then for the sodium borohydride, it's going to look very similar. Just replace this with sodium borohydride. Oh, there's a sodium ion hanging out. See how that is negative charge? That negative charge attracts the lithium ion. So for the borohydride, just change that to a B. For boron. And it does the same thing. God, I can't believe I just messed up that arrow. I am so tired, and all of these are molecules, and arrows are starting to look alike to me at this point in the day. Goodness. That's the last slide we needed to cover. We'll do carbon nucleophiles in the next Zoom video. Goodness knows I need to take a break before I dive into Grignard reagents. There's that chapter reference. And then the Wittig reaction. You can say it Wittig or Wittig. Wittig is probably more correct since that's generally how these are said in Germanic languages and Scandinavian languages. Notice there's a Nobel Prize. These are the two most important reactions for you to learn in the chapter, maybe in the next video. But you see how many slides that Grignard is? That's why I don't want to cover it right now. If you really had to boil this chapter down to learn only one reaction, learn the Grignard. That's even on the MCATs. Okay, so let's go. I'm going to get back to here. So we got to this one. We went. And then the final part will be all of this. That'll be just like a part 4 video. Only because these last two, they don't take up much time. What takes up time is this. I don't know, maybe I'll end up separating them into two parts. I don't know. But this is where we have finished at this point.